Okay, welcome to chapter 11. We are going to start out looking at some average velocity problems. Okay, so average velocity is the change in position divided by the change in time. And we're going to do a couple examples here so that you can see how this is really something similar that you actually already know how to do. Okay, so in this first problem, it tells you that an automobile travels 120 miles in 2 hours and 30 minutes. Okay, so again, average velocity is the change in distance or position over the change in time. Okay, so in this case, my change in position is 120 miles. It moved a distance of 120 miles. Okay, so that's going to be 120 miles over the change in time. Well, here, the change in time was 2 hours and 30 minutes, or 2.5 hours. Okay, that means that if I divide this out, my average velocity, which you can see is a miles per hour kind of a thing in this particular example, my average velocity is 48 miles per hour. Okay, now, here's the problem. Um, if the average velocity is 48 miles an hour, does that mean that they remained at 48 miles an hour the entire trip? And it does not necessarily mean so. Okay, it did not say that they traveled at a constant speed. I'm just asking you for the average velocity. That means there might have been times when they were going crazy fast during this 2.5 hours, and there might have been times when they were going really slow during this 2.5 hours. But over the course of the 2 hours and 30 minutes, on average, when I average their speeds out, it gets to be 48 miles an hour. So this little method does not help us find what was the car's speed 1 hour into the trip, or what was the car's speed 30 minutes into the trip. Okay, this method does not help us do that. And so the next question is, what was the instantaneous velocity 1 hour and 15 minutes into the trip? That's asking me if I can figure out what is the speed of the car 1 hour and 15 minutes into the trip. So the method that I used is not going to work to do that. And so we're going to kind of look at this long battle here of how to answer that question. And this is kind of the root of how calculus was started. Okay, so moving on to kind of a different example. I don't have a way right now to answer this question, what was instantaneous velocity? So I'm going to teach you a method so that you can kind of figure this out with a different example. Okay, if you think about this, if we freeze time, at 1 hour and 15 minutes. If we freeze time, that means the object that is moving has to be frozen too, in theory, which means it's not going to have a velocity. Okay, so you need another method, and here's what it is. Kind of a different example. This is telling you that a ball is moving down the ramp, and the formula t squared measures how far the ball is down the ramp by time. Okay, so it's saying that the distance from the top of the ramp is time squared. Okay, so if you're 1 second, you're 1 squared or 1 foot down the ramp. If 2 seconds have passed, then you're 2 squared or 4 feet down the ramp. Okay, what I did is I sort of graphed the formula t squared, or the function t squared up there so that you can see. Okay, so now really, in order to answer this question about instantaneous velocity, what they did in calculus is they started looking at really small increments of time. Okay, so in this example, I'm going to look at how the position changed from 3 to 4 seconds. Okay, so I'm going to look in this little interval right in here. I'm going to look at just this little interval right in here for the first time. And I'm going to ask you what is the instantaneous um, velocity from 3 to 4. Okay, that means I'm going to do this, the change in s over the change in t. Okay, remember that s is t squared. I just want you to know that. Okay, so that means if I'm going from 4 seconds to 3 seconds, um, I'm going to go 4 squared because my formula is t squared minus 3 squared over t, which is 4 minus 3. And I should probably show you this, okay? Think about this as coordinates. You're probably a little confused, sorry. Think about this as coordinates. if 2 seconds have passed, then your y value is going to be t squared, okay? So 2 squared is 4. If 3 seconds have passed, 3 squared would be 9, okay? If 4 seconds have passed, 4 squared would be 16. You can think about it like that too, okay? I am trying to go between 3 and 4 seconds. So really what I'm doing is I'm figuring out that slope, and I will have 16 minus 9 over 4 minus 3. 16 minus 9 is 7, 4 minus 3 is 1, and I get 7. Okay, now what I'm going to do is I'm going to go up and I'm going to make the interval that I'm looking at smaller and smaller and smaller. So first I did from 3 to 4. Okay, now I'm going to make it smaller and I'm going to go from 3 to 3.1. So I'm just going to go this teeny tiny little area right in here from 3 to 3.1. Okay, so here we go. I'm going to make a coordinate here so that we can figure this out a little bit easier, okay? So when my time is 3 seconds, then I take 3.1 and square it, and 3.1 squared is 9.61, okay? When I take 3 and square it, obviously I get 9. So if I were to do this, I can go 9.61 minus 9. Oops, this should have been 3.1. Sorry. 9.61 minus 9 over 3.1 minus 3. Okay. When that happens, I get 0.61 over 0.01, which is 6.1. Okay, now I'm going to make that interval even smaller. So I'm going to go back up here and I'm going to look at even a tinier chunk. Okay, I'm going to look at this tiny, tiny chunk right in there. And that is from 3 to 3.05. Okay, so we'll try this again. When your time is 3 squared, since that's my function, is 9. Okay, when I do plug in 3.05, when I square 3.05, I get 9.3025. And again, I'm squaring them because my function is t squared. If my function were 2t, I would multiply your x value by 2. If my function were t to the 5th minus 1, I would take my x value to the 5th power, subtract 1 to get my y value. Okay, but that's all that's happening. Now, I'm really doing, again, change in position over change in time, which is really nothing more than doing slope. So 9.3025 minus 9 over 3.05 minus 3. When you simplify that, you get 6.05. Okay? Now, here's the deal. I want to know what the velocity is. My grand question for this whole thing is, what is the instantaneous velocity at exactly 3 seconds? Okay, we talked about how you can't really find it quite exactly at 3 seconds because if you freeze time at 3 seconds, technically the object is frozen too. So what you want to do is you want to look at closer and closer and closer increments to that actual number. Okay. So I'm getting closer and closer and closer to 3. I want you to notice that to begin with, I started with 2 points that were this far apart. Okay? Then I moved to 2 points that were like that far apart. Then I moved to 2 points that were super close together, and they were like that. And basically, when you look at these little points right here that are super duper duper close together, that's about as close to 3 seconds as you can get. The distance between 3 and 3.05 is basically 3, okay? So you're getting closer and closer and closer to the actual number and kind of estimating. And what you should notice in this problem is that your numbers are getting closer and closer to 6. It started at 7, and then it went to 6.1, and then 6.05. If I did 3 and 3.005, my number would be even closer to 6, okay? But we need to kind of have another way to do this without sitting in actually plugging in 85 million points and trying to come up with a pattern. That is how we got this little problem, okay? If we continue this process and we used smaller and smaller intervals to look at until our intervals got really close to 3, okay, we would see that they're approaching 6. Here's how we would do that, okay? If we think about this, and we think about it algebraically, okay, we want our time to approach 3 minutes. It's never going to be 3 minutes exactly, but we want our time to approach 3 minutes, okay? We're using this kind of handy-dandy little formula right here. And this is what's going to happen, okay? Our time is 3 minutes, so obviously this right here is our x value, okay? This is our y value. When we plug it into the function is t squared, so these are our y values, okay? Sorry, that's not right. This is an x value. Okay, when we plug into the function, which is t squared, obviously if you take t and square it, you get t squared. If you take s, or you take 3 and square it, you get 3 squared, which is 9. Okay, so I'm kind of plugging this in so that it can work. Okay, so this is saying as my intervals approach 3, okay, then what's happening is I have my function squared minus the x value that I want, which is 3 squared, over my time difference, which is my, I don't know my time, minus 3. When you do this, you get t squared minus 9 over t minus 3. Okay, which really gives me, and I should have write the limit over, which really gives me the limit of t plus 3, t minus 3 over t minus 3. Those will cancel, which gives me the limit as x approaches 3 of t plus 3. And then think about putting that in. It should be t approaches 3. Put the 3 in right there, and you get 3 plus 3, which is 6. Okay, so we say that the instantaneous velocity as this object approaches 3 seconds, or is at about 3 seconds, is 6. Okay, it gives us the best estimation that we possibly can have. All right, we're going to do another one now with a different function. Okay, so now this is saying let the position of an object at time t be given by this function right here. And then find the instantaneous velocity at t equals 2. Okay, so you're going to start out like this. The limit as your time approaches whatever it is you're wanting to find. In this case, it's 2. Okay, I'll kind of show you how to do this without doing all of the little steps that are off to the side, but if you want them to be off to the side, you can. Okay, so what you're first of all going to do is you're going to start by just plugging t in. Okay, when I plug t in, then I have 4t minus 5. I'm going to subtract that. I'm going to subtract now when I plug 2 into that function. When I plug 2 into that function, I have 4 times 2, which is 8, minus 5, which is 3. Okay? And then I have t minus 2. If you can think about that, what you've really done is you've really made yourself 2 coordinates. One of them is t. When you plug that into the function, you get 4t minus 5. The other one is 2. When you plug that into the function, 4 times 2 minus 5 is 3. Okay? And then you're really finding slope. Okay? Think about this as your y2. This is your x2, sorry. This is your x1. This is your y1. And you're really finding slope. Okay? y2 minus y1 over x2 minus x1. That's really all you're doing. When you simplify this little guy here, your limit as t approaches 2 becomes 4t minus 8 over t minus 2. And then, of course, you can factor that so that the limit as t approaches 2 becomes 4 times t minus 2 over t minus 2. And then the t minus 2's cancel out, and all you have left is 4. So I don't even need to take that t and plug it in. I just get 4. Okay. All right. A couple more little things. When we write the limits, what we mean is that f of x gets extremely close to L as x gets extremely close to A. It can never be exactly that, but it's what happens as it gets really, really close to it. So when we do limits, this is kind of what we do. We start with 2 points, and that's what we did in our first example that we did. We start with 2 points that are a little bit farther apart. And then when we do the limits, what we're really doing is we're moving these 2 points closer and closer and closer together. So then next time I might do this point and this point. Okay, they're a little closer. And the next time I might do this point and this point. They're a little closer. And eventually you're going to get to points that are super duper, like super close together. 2 points that are super close together. And if I connect them, I basically get a point that goes on the outside edge of your curve, which is called the tangent line. Okay? And that's really what we're doing when we do this. Okay, so this is giving us a function, y equals x squared. It's asking us to connect the points 1, 1 and 2, 4. Okay, if I connect them, notice that line, sorry, that's a little crooked. That line goes on the inside of that curve, and that's called a secant line. Okay, it connects 2 points that are on the curve. It's not on the outside edge, but that's what it is. Now, I'm wanting to find the slope of the secant line. So to find the slope, again, you're going to do y2 minus y1. So 4 minus 1 over 2 minus 1, which is 3 over 1, which of course is 3. Okay, now I want you to find the average velocity when between the intervals when x is 1 and x is 2. So these are both x values. This is x1 and x2. Think about coordinates, okay? If you have 1 and you plug it into the function y equals x squared, if you have 1, you get 1. If you plug in 2, 2 squared is 4. And now if you find the average velocity, you're really finding the slope between those 2 points. So the average velocity would be 4 minus 1 over 2 minus 1, which is 3 over 1, which is, of course, 3. So in general, how could you represent the average velocity of ball over the time interval A, B? So in other words, if you don't have numbers in there and you wanted to just put letters in there, this is what I'm telling you, okay? If your 2 point, this is what I'm going to tell you, okay? It's the slope of the secant line through, okay, if you have A, f of A will be the result that you get when you plug A in, and B, and when you plug B in, you're going to get f and B, f of B, okay? What that is the change in y, basically, over the change in x, which is just f of B minus f of A over B minus A, okay? That is what happens because, again, this is your x1, y1. This is your x2, y2. You're really doing nothing more than finding slope, okay? And here's slopes of a bunch of tangent lines, just so you know. Okay, here is that formula written for you right here. But again, the average rate of change on an interval is you're basically finding the slope. When you have one x value, what do you get for your y value? When you have another x value, what do you get for your y value? Rate of change is nothing more than finding the slope. Okay? And that should do it for this lesson.